In this lecture, we're going to look at new terms related to how reactions can proceed when there are multiple sites and stereochemical opportunities that are possible. And so the first term that we're going to look at is regioselectivity. So I could define regioselectivity right away, but let's just first start by introducing the idea as one that only applies when a reaction can happen at multiple sites in a molecule. Okay, so the best example I can give you is the epoxide. There are numerous examples of this, but if we have an epoxide, we can have a reaction here, or we can have a reaction here. So either the left side or the right side, and if we introduce some other groups to destroy the symmetry of the molecule, those two opportunities for reaction would be different. So a reaction can be regioselective. It's kind of a property emergent among reactions as opposed to molecules. But we could say that a reaction is regioselective if it can favor one site over another. And some plural regioselective reactions can favor one site over another. So if we look at this in context, we would say that ring opening of epoxides under basic conditions So we're focusing on the basic conditions first, and I realize I need an S on that. Favors or is selective for nucleophilic addition at the less substituted position. And that position that I'm referring to is the carbon atom. So the less substituted epoxide carbon atom. Okay. And if we're specific about that, we could say, if we use our go-to epoxide, we could say, well, if we add some RMGBr, where we consider the MGBr as sort of a counter ion to a carbanion, not the most rigorous definition of a Grignard reagent, but really helpful. We're going to favor substitution where the R group, or ring opening, where the nucleophile adds to the less substituted position, and that's going to be the position without the methyl groups in this case. So that's going to kickstart our reaction so that we get to something like this. We follow that up with then H plus, we get to this product, okay? So we could have some parallelism here for the acidic conditions. Ring opening of epoxides under acidic conditions. Favors slash is selective for addition to the more substituted epoxide. And I should clarify that we want to do this through or by way of a protonated epoxide intermediate. So this is me just reminding us that the protonated epoxide is involved here. Forgot the key word there, more substituted, excuse me. So the more substituted epoxide carbon atom. And this is because the epoxide, once it's protonated, becomes distorted. We've addressed this before, but it's an important concept. Protonated epoxides distort or are distorted to lengthen the CO bond at the more substituted carbon. Okay. Now, when we distort this, it's going to make one side look more appealing for a reaction center than the other side. So the first step, let's just go ahead and draw the protonation step. So we have some sort of acid that's present from one of a number of sources. Now, after the epoxide gets protonated, sometimes I draw it as a right triangle so that I can see. Now we have an epoxide that's distorted to lengthen and weaken the bond to the more substituted position, which has the two methyl groups. And so what this does is this means that when the nucleophile comes into attack, there's a number of ways to look at this. The nucleophile could attack a carbon with a weaker bond to the oxygen that needs to ring open. So there's a weaker bond to break, making this a pathway that requires less energy for the nucleophile. You could also say that the distorted epoxide looks a lot more like the transition state. So after it's distorted, it looks like the transition state preparing itself for the nucleophile to add at that side over the opposite side. But either way, now the energy difference between the two sites is not determined by sterics, but it's determined by the geometry of the protonated epoxide intermediate. And so the nucleophile adds to the left, and that's going to put our OH on the right, or at the more substituted position. So a way of thinking that's incorrect about why epoxides distort is to consider carbocation stability. So epoxides that are protonated epoxides, will distort such that a more stable cation could form. Now, what I'm getting at is if we protonate the epoxide, and let's not let it distort, but we have two choices. We could distort or lengthen bond A or bond B, A on the left and B on the right. Let's consider something, an alternative. What if we break A and we push A up and onto the oxygen? If we break A, then we get to, that protonated, excuse me, a tertiary carbocation. And as we had talked about when we were looking at tert-butyl ethers being cleaved under acidic conditions, that this is more stable, so very stable. Whereas if we break B, and so B jumps up and onto the oxygen, then we have a situation that looks like this, where we now have a cation that only has one group attached to it. So we would call that a primary carbocation, put a 1 with a degree next to it. So this is highly unstable, especially relative to that tertiary carbocation. Now, here's the thing. This is a really helpful sort of mnemonic or shortcut to figure out which of the two carbon atoms will be more likely to be distorted and build up greater positive charge and be more likely to accept a negatively charged nucleophile, but it doesn't happen. So such that a more stable cation could form, but this doesn't happen. I don't include carbocations in my mechanism because they do not form. So this comes with a huge caveat, but the carbocation doesn't form. Some folks like to consider a carbocation as an intermediate in their mechanism, but that's not right. We have evidence going against that. And that's okay. We're all just discussing models. We make hypotheses. Hypotheses are wrong. It's nothing against it, okay? It was a really good proposal. It just turns out that it's not correct. So when we think about these molecules, we have to take that into account, build that into our model. And instead of thinking about a carbocation being formed where plus and minus charge adding to each other makes a lot of sense, instead we have to think about it as a buildup of positive charge as the molecule becomes distorted. So it becomes distorted. That allows for a buildup of positive charge, in this case on the left side, as we weaken that carbon-oxygen bond and the oxygen atom draws more and more, I'll leave that up, more and more of the electron density. Now why? How do we know that we don't see a carbocation intermediate? It has to do with the stereoselectivity. So stereoselectivity is the reason why we know that protonated epoxides don't involve carbocation intermediates. So stereoselectivity, this is the preference or the preferential formation of one stereoisomer over another. Okay. Now what kind of is just required is that if a carbocation is involved, carbocations are, I think, as far as I can tell, I can't think of a really good example that's not super complicated, but carbocations in general are not chiral. Carbocations are flat, and if they're flat, they have a plane of symmetry. Are flat, that is planar. They're sp2 hybridized. And achiral. Now we've seen this before when we had a, if we put a phenyl and a methyl and an ethyl and a bromine, and we do some sort of SN1 reaction. So let's do an SN1 with methanol, or let's just have a generic nucleophile. I want to focus the issue. Okay. So we have some nucleophile. So if we do an SN1 reaction, not worrying about E1 for a second, the bromine is going to leave, and that's going to give rise to this carbocation. This carbocation does not have 4 different things attached to it. It is achiral. We started with something that was not only chiral, but it was a single enantiomer. It was a single stereoisomer. When the nucleophile adds, the nucleophile could add to the top or the bottom. If it does top attack, we'll see the nucleophile form a wedge. If it does bottom attack, the nucleophile will form a dash. Okay? So what this tells us is that when a carbocation is involved, we lose the stereochemical information. That is to say that we started with our bromine as a wedge. When we do the SN1 reaction, is the nucleophile going to be a wedge or a dash? Well, it's going to be both. The molecule kind of forgets that it was a wedge altogether as it goes through a planar achiral intermediate with opportunities for both the top and the top and bottom attack to give a wedge or a dash respectively. And that happens anytime we involve a carbocation. So the fact is, if you observe any stereoselectivity, you have to rule out a carbocation intermediate. If a reaction is stereoselective, it cannot utilize a carbocation. Okay. So that is our reasoning why a carbocation can give rise to or a stereoselective reaction cannot involve a carbocation. That is, if we preferentially form one stereoisomer over another, we cannot involve a carbocation. Now, why is that important / relevant? Well, it turns out that if we add some chirality to an epoxide, let's change one of those methyl groups for a phenyl group, a benzene ring, which we label as pH. We're going to replace, and then we're going to add some H plus some nucleophile that I'm not going to worry about right now. We get only a single outcome of a product. We get a product where the phenyl is a wedge, the methyl is a dash, and then the nucleophile is a planar line along with the bond from the carbon, along with the carbon-carbon bond going to the oxygen that was once part of the epoxide. So this is our only stereoisomer. Our only stereoisomer that's formed. And if we only have one stereoisomer, I just have to emphasize this again, we don't involve a cationic intermediate. Now, what's the mechanism for the formation of that stereoisomer product? Well, the mechanism is as follows. First of all, we protonate the epoxide to give a protonated epoxide. So I'm going to draw phenyl with a wedge and methyl with a dash. And then we're going to show H plus the nucleophile. Now the oxygen is going to add to the hydrogen to give us our protonated epoxide. I can draw it with a little bit of distortion. The right triangle will exaggerate, so it's not a little bit, it's a lot of bit of distortion. So the right triangle now has this exaggerated, and we can have the hydrogen hanging off as a positive charge. Okay. And even with the phenyl group, we still don't fully see this epoxide do a ring opening process to form a cationic intermediate. Instead, what happens is it locks in at this distorted structure and the nucleophile engages. Now, here's how the nucleophile engages. It comes underneath and attacks along a plane of trajectory that's opposite that of the carbon-oxygen bond that it's attacking. So it's going to kind of squeeze in here and push that bond up. Okay, that's sometimes hard to picture. So what I do instead is I go sweeping underneath. I go sweeping underneath, and I make sure to always crawl underneath the two groups that are shown as a wedge and a dash, and then I spring the oxygen open. When I do that, I always get my stereochemistry right, because if I go underneath attack, my phenyl stays a phenyl, or excuse me, my wedge stays a wedge and my dash stays a dash. Let me show that to you. Okay, so we ring open the epoxide. I'm going to show my OH sitting over here. Here's where my nucleophile. Now I have to add my phenyl and my methyl group and define the stereochemistry with good precision to make sure I get the stereochemical information right. What's going to happen is, well, if we look, we have a tetrahedral center with a wedge and a dash offset the two planar lines. Okay, the wedge is actually going to stay the phenyl and the dash is going to stay a methyl. And you might be saying, oh, If I just draw the nucleophile adding underneath, I don't have to worry about anything like inversion of configuration or backside attack. It turns out though, and I'll just say this, I'm not going to write it, inversion of configuration and backside attack do happen. This is a very similar type of transition state as the SN2 reaction. But what we're doing is we're showing the nucleophile crawling underneath, and all we're doing is we're sort of taking our wedge and our dash and flipping them up so that we still have a tetrahedral geometry. But what was a wedge stays a wedge. What was a dash stays a dash. We actually, by flipping them up like this, we do the inversion process ourselves without having to worry about flipping wedges and dashes around. So you just add the nucleophile underneath, take the stereocenter, push it up, and you'll get the stereochemical information right because it will match the starting material under that drawing depiction. Okay. So we show this formation of the single stereoisomer. Under basic conditions, the reaction is also stereoselective. In fact, we would say it's, well, I won't get into it. It's, for the record, it's stereospecific. It's specified by the starting material. But let's just stick with stereoselective. It's kind of like a square is a rectangle, but a rectangle is not a square. Or wait, no, a square is a rectangle, but a rectangle is not a square. Okay, I did it right. So the reaction is also stereoselective at the less substituted position. Okay, so what's a substituted position versus a less substituted position? Well, you just sort of count the things attached. Don't worry about the bulky size, but I don't want you to get tripped up and worry about this. So sometimes, okay, let's say we've got phenyl, and we've got methyl, and we've got methyl. So I'm going to go ahead and write Me for methyl here, and I'm going to add this to RMGBr, but I'm going to cross out the bond and the MGBr, replace it with a negative charge, just so I can keep track of what's happening here. The negative charge is going to engage the right side of the epoxide now. This is regioselectivity towards the less substituted position we talked about earlier in the lecture. That's going to spring the epoxide open on this side. Let's go ahead and draw the resulting outcome of this. Now, the left side of the reaction stays unchanged. The phenyl group stays down in this case as a wedge, or wedge pointing down. The methyl group stays a dash. Everything really keeps its wedge dash integrity as long as you attack the nucleophile underneath. So here the R group is crawling underneath the methyl along with, we didn't have to draw it, but the wedge to the hydrogen. What I'm going to do is I'm going to take my hydrogen and my methyl group and just spin them up as the nucleophile is coming into attack. That is, look at it this way. The R group comes in underneath. That forms our new bond. We have two lines, two planar lines, and now we have to add a wedge and a dash to form the final tetrahedron. Well, the wedge just was a hydrogen, stays a hydrogen. It's just pushed up, same with the methyl group. That retains our overall tetrahedral geometry without worrying about how to scramble the stereocenters and all of that. Inversion of configuration backside attack happens then in the background. We don't have to worry about kind of keeping track, doing RNS and that sort of thing as we flip these things around. The last thing we'd want to do is add a little NH plus to quench the reaction, work up the reaction, and neutralize our charges. And that gives rise to our final product as a single stereoisomer. Okay, so that is looking at stereoselectivity and regioselectivity for epoxide ring opening reactions. That is, it kind of changes whether you're under acid or base conditions for the regioselectivity, but the stereoselectivity remains the same. The nucleophile adds underneath, the carbon-oxygen bond to be broken, then we just take our wedge and our dash and just push them upwards. So that'll do it for this lecture. I'll see you next time.